Beneath the sleek surfaces of our devices, an unseen architect has reigned supreme for half a century. Silicon. Its simple, elegant structure has fueled an exponential leap in computing power, making the impossible commonplace. But for how much longer? A shift is underway, a quiet tremor at the very bedrock of our digital existence. What if the material we've relied on, the very essence of the modern transistor, is finally reaching its fundamental limits? And if so, what takes its place? The answers are emerging, not from incremental improvements, but from entirely new chemistries in physics. The future of computing depends on it. Silicon's dominance wasn't accidental. It possessed a unique combination of qualities: abundant, cheap, and remarkably resilient. Its high melting point allowed it to function reliably at elevated temperatures, crucial for any power-hungry system. Even more significant was its dopability, the ease with which engineers could introduce impurities to precisely tweak its conductivity, shaping the flow of electrons with exquisite control. This versatility, this inherent adaptability, propelled an era of unprecedented technological growth. But the very strategy that defined this golden age, the relentless shrinking of its components, now presents an insurmountable challenge. For decades, Moore's law has been our guiding star, promising a doubling of transistors every 2 years. An exponential march towards ever faster, ever smaller computers. But that law, once absolute, is now colliding with an invisible wall. Not an engineering hurdle, but a fundamental barrier of physics. At just 2 nanometers, the gate of a silicon transistor is roughly 10 silicon atoms wide. We've crossed into a realm where quantum mechanics, with its unpredictable rules, begins to set the limits. The classic strategy of shrinking silicon further is failing. The question is no longer how to shrink, but what to shrink, and on what materials. This isn't just about finding a better silicon. It's about a complete paradigm shift. A reimagining of what a chip even is. The demands are relentless: faster switching speeds for electric vehicles, higher voltage tolerance for renewable energy systems, better thermal efficiency for high-performance computing. Silicon, despite its past triumphs, simply cannot deliver these extreme requirements much longer. We're witnessing not the end of innovation, but the end of one era, and the tantalizing first breath of several others. The race is on, not merely to replace a material, but to redefine computing itself. One promising contender has already emerged, stepping out of silicon's shadow. A new transistor, developed by a team of scientists, has dared to ditch silicon entirely. Instead, they opted for a material known as gallium-doped indium oxide, or NGAOX. This isn't just a tweak, it's a foundational change, offering the potential to leave silicon in the dust. Their detailed findings, set to be unveiled at the 2025 Symposium on VLSI Technology and Circuits, hint at performance breakthroughs that could redefine high-efficiency power systems and signal a new direction for integrated circuits. A crucial step, but only one piece of a much larger puzzle. But what if the answer isn't just a new material, but a new dimension? Enter molybdenite, or MOS2. This inorganic compound, composed of molybdenum and sulfur, boasts an astonishing property: it can be fabricated as thin as a single monolayer sheet. Imagine a transistor that uses 100,000 times less energy in standby than traditional silicon. MOS2 promises exactly that, already demonstrating its capabilities in flexible electronics and even simple microprocessors. Its ultra-thin structure could unlock unprecedented miniaturization and energy efficiency, offering a path to power-sipping devices we can only dream of today. Graphene, another two-dimensional material, also looms large in this evolving landscape, hinting at a future shaped by atomically thin layers. The search for silicon alternatives extends even further into the periodic table, revealing more exotic compounds with extraordinary potential. Chinese scientists, for instance, have unveiled what they've dubbed the fastest transistor ever. The secret? Not silicon, but a channel made from bismuth oxychalcogenide, paired with a gate material of bismuth selenide oxide. This bold departure showcases that innovation isn't confined to a single material class. The entire elemental palette is being explored, each new combination offering unique properties for speed, power, and thermal management. These breakthroughs signal a relentless pursuit of the ideal semiconductor, one that moves far beyond our current understandings. While new materials redefine the transistor, entirely different physics are also emerging. Quantum computing isn't about replacing the transistor, but augmenting it. It's a parallel universe of computation. Intel's spin-qubit processors, IBM's 50-qubit Q, and Google's 72-qubit bristlecone are pushing the boundaries of what's possible. Yet, these marvels operate at temperatures near absolute zero, demanding cold computing environments. It's a powerful tool for specific, complex problems, but it won't be in your next smartphone. Quantum represents a leap, not a replacement for the workhorse transistor, but a symbiotic evolution. One that hints at a multifaceted future for computing. So, what replaces silicon in 2030? The truth is, there won't be a single answer. The future is not a monolithic silicon replacement, but a diverse ecosystem of specialized materials and architectures. Indium gallium oxide for power systems, molybdenite for ultra-low power devices, exotic bismuth compounds for speed. And alongside them, 3D architectures and heterogeneous integration will push existing limits, even with silicon. 2 nanometers isn't the future, but the end of one path. 2030 heralds the first breath of several others, where the chip becomes a complex, hybridized tapestry of specialized materials. The transistor isn't dead, but its material will evolve, fragmenting into specialized forms, each uniquely suited to the challenges of the next computing era.